Since the calculator only has logarithms of base 10, logarithms of base e contained within them, we might wonder how in the world we're going to figure out this problem, the log of 9 in base 3. Well, we certainly know the answer to the problem. It's the exponent applied to 3 that will give 9. 3 to what power gives 9? Well, 3 squared is 9. But let's talk about a technique for using the calculator to evaluate this. It turns out that we can actually change to any base that we want to by using this technique. That is, we can change to base 10, we can change to base e, we could change to base 7 or whatever we'd like. But if we change to base either 10 or e, then we can evaluate this expression in the calculator. And it just involves this. It involves making a fraction. Now, I'm changing to base 10 here, and notice I have log base 10 of 9 in the numerator, and I have log base 10 of 3 in the denominator. And the 9 and the 3 are the numbers that happen to appear up here. Now, we're not going to look right now at why this is the case. We're just going to say, okay, this is the change of base formula. It is a formula for changing the base of logarithms. All right, now, and for evaluation purposes, we would put this into the calculator, log 9, then divided by log 3, and then press enter, and 2 will pop out. Now, another way to make the calculation is natural log of 9 over the natural log of 3. And again, this quotient will end up being 2. Now, if we wanted to change to, let's say, a base of 7, then I could change this to base 7 like this. I could say, okay, log base 7, and now log base 7 of 9 goes in the numerator, log base 7 of 3 goes into the denominator. So we have changed the base of this expression to 7. Now let's go through the calculation with the calculator one more time. If we're evaluating using the calculator log of 5 in base 2, then we can work it one of two ways. If we're using common logarithms, then we would enter log 5 over log 2 and press enter, and we get an answer. If we want to use natural logs, we enter ln 5 over ln 2 and we get the same result. Now I want to emphasize the idea that although these quotients are exactly the same, the numerators are different and the denominators are different, but the quotients are identical. You see, these are the approximate values for numerators and denominators here, and yet the quotients turn out to be 2.32 in both cases, as we would expect. Now, the proper interpretation here is that 2.32 is the exponent on 2 that will give 5. That is, 2 to that power will give 5. Well, we may realize at this point, and we've looked at it from several perspectives, that a lot of our situations, a lot of our properties involving logarithms have as their basis some kind of idea in the exponential world. And we didn't specifically say this, but something like the log of 1 being equal to 0, we know this is true because a to the 0 equals 1. You see, in the exponential world, you take a base and raise to the 0 power and you always get 1. Change that situation into the logarithmic world and we have this, you see, base exponent, 1. All right, so no wonder this works out in the logarithmic world. It has a basis in the exponential world. Now, the next several properties we're going to look at also have a basis in the exponential world. We know that in the world of exponents, if we multiply like bases, we add exponents. When we divide like bases, we subtract exponents. And when we raise powers to powers, we multiply exponents. Well, each of these ideas in the exponential world has kind of an equivalent idea or a related idea in the world of logarithms. Now, they don't appear, though, to be related. It doesn't look like this kind of stuff, but this is the basis for them. 3 properties we're going to look at right here. And right about now, as soon as we look at these, it creates a certain amount of confusion. And a few questions arise. Why do we need to learn this? And what are we doing this for? And I can't see through this and all that kind of stuff. But just realize that just with a little experience here, all of this will become clear. And we'll be able to use these properties very simply once we get a little bit of experience with them. Okay, First of all, the product property. This is the one that's related to the idea that when you multiply like bases, you add exponents. And it's this: the logarithm of a product is equal to the log of one factor plus the log of the other factor. Doesn't seem to be any relation whatsoever to the related exponential form, but remember, we're dealing in the world of exponents. And in the world of exponents, when you have a common base and you're multiplying, you add the exponents. That's an exponent, this is an exponent. That's kind of the basic idea. Now, you're not going to remember it like that. You're going to remember it like this, that when you're taking the logarithm of a product, you can rewrite that as the log of one factor plus the log of the other factor. And we need to also be able to go the other way. There are circumstances where we need to expand and other circumstances where we need to sort of contract this expression. So when we have the sum of two logarithms and the bases are the same, then we can write this as the logarithm of a product, the log of the product of 5 and x. Now notice I'm not writing a logarithmic base here, and I'm doing that because I don't want to add confusion to the situation. But this property works for all bases. It could work for ln, for example. It could work for log base 7, log base 5, whatever, as long as the base is the same in all of these expressions. Okay, the quotient property. The quotient property works like this, that when we are dividing and we have like bases, we subtract exponents. Okay, when we take the logarithm of a quotient, it is the difference of logarithms. It is the log of the numerator minus the log of the denominator. And for the power property, the one way raising power to power, we multiply exponents. Well, it's the idea that we have the log of x to the 5th power. We can write 5 as the coefficient of log x. This is 5 log x. And we can go the other way. That is, if we have 5 log x, this is the log of x to the 5th power. So this is just a two-way street here. Same idea with this. If we have the difference of two logarithms in the same base, then we have the logarithm of a quotient, and it's the quotient of this rascal over that. Okay, now I would love to give an easy proof for these and a nice, good relationship for us to remember this, but there isn't one. I'm going to show you how this comes about, and I'm going to relate this back to the exponential form, but it's not the kind of proof that you would tend to remember very much. But let me show it to you. Let's take this expression and just put it up here. All right, now just follow this little discussion. Suppose we just let log 5 and log x have a relationship to a variable or to a letter. I'm going to let A stand for log 5 and B stand for log x. Now that allows us to change each of these to an exponential form. That's the purpose of doing this. So this is equivalent to, or implies, let's see, now I'm using the common log base of 10. If I use 7, it would work out the same way or whatever, but I'm just using log 5. No base is indicated, so it's understood to be 10. So we have base exponent equals 5. So 10 to the a power is equal to 5. And here, if b is equal to log x, then 10 to the b power is equal to x. All right, now, let's go through and make some substitutions. We have log 5x means, well, what's 5 and what's x? Well, over here, 5 is 10 to the a power and x is 10 to the b power. Okay, so if 5 is 10 to the a and x is 10 to the b, then we have this. But we know that when we're multiplying like bases, we add exponents. So we have 10 to the a plus b. And the log of 10 to the a plus b, we know from before, from the last section, that if the logarithmic base and that number are the same, then we simply have a plus b. But what is a plus b? You see, we simply have that exponent, a plus b. But what are a plus b? Well, a and b are log 5 and log x. So a is log 5, b is log x. And so log 5x is log 5 plus log x. Now, once again, I'll mention that this kind of looks like smoke and mirrors right now. And that confusion, if there is any, is expected at this point. But with a little experience, it'll all become clear. Let's use the properties of logarithms to expand a few expressions. If we see the log of a quotient, we know it's the log of the numerator minus the log of the denominator. So this is simply log in base 2 of the numerator minus log base 2 of the denominator. And that's all there is to it. In this one, we can approach this problem in a couple of different ways. But one way, and I think the simple way to understand it, is like this: log base 2 of 8 to the 1/2 power. Now I'm just taking the radical and writing it as a fractional exponent. And that allows me to use the power property. Remember, I can take this exponent and I can write it over here as a coefficient. So this becomes 1/2 log base 2 of 8. Aha, but 8 has multiple factors in it. I can rewrite 8 as 2 cubed. So I have log base 2 of 2 cubed. Oh, I can use the power property again. 3 then becomes another coefficient out here. So this becomes 3 times 1/2, or 3 over 2 log base 2 of 2. But when these two numbers are alike, we know that this becomes 1, and so this is simply 3 over 2. In this problem, we have the logarithm of a quotient. Now, notice it's natural log, but it doesn't make any difference. The base of the logarithm makes no difference in these properties. So we apply the properties kind of universally. So natural log of a quotient means the natural log of the numerator minus the natural log of the denominator. Now we see we have the logarithm of a product. So this becomes ln 3 plus ln x squared, and I'll bring down minus ln y. Oh, but here we can use the power property to write 2 as the coefficient, so this becomes ln 3 plus 2 ln x minus ln y. On this one, now we begin with the idea that we have a product, so we have ln y plus ln, you see we're applying sort of the logarithm to each of the factors. So it's ln this factor times, plus ln that other factor. So it's plus ln this other factor, y minus 1 squared. And now we can use the power property to rewrite this expression, or this term. This is ln y that I'll bring down, and then plus, this becomes the coefficient, so 2 ln y minus 1. Now, I think at this point, when working with properties of logarithms, I find that with my students, it's just as important for them to know what they can't do as it is for them to know what to do. Because there's a tendency to try to use some techniques that have been learned in the past and apply them here in the world of logarithms, and they simply don't work. For example, the idea of distributing this notion of logarithm, this operation of logarithm throughout this binomial, and think of this as ln y minus ln 1. Well, that just doesn't work. The logarithm idea doesn't distribute. Other operations don't distribute as well. Now, this doesn't work any more than the notion of having the square root of x minus 1 giving us the square root of x minus the square root of 1. Does this work? No. So this doesn't work either. You see, there's no distribution idea in this notion of logarithms. Also, let me point out another frequently made mistake. We dealt with a fraction up here. All right, now let me show a fractional situation. When we have, let me use a simpler one. If we have simply log of x over 5, then we know that this is log x minus log 5. Okay. There's a big difference between this and this. Log x over log 5 is a completely different thing than that. And in this situation, we can't cancel these logs. We can't cancel log with log and have x over 5. That just doesn't work out. This is an operation symbol. We can think of it like that. If this were the square root of x over the square root of 5, could you cancel those radicals? Of course not. You see, so be careful with that. And this doesn't illustrate our quotient property. This illustrates the quotient property. It's the logarithm of a single quotient, you see, not the quotient of logarithms like this. It is the logarithm of a single quotient that gives us the difference of two logarithms. All right. Up here, it's valuable when radicals are involved to use the fractional exponent idea. For example, here we can rewrite this as the natural log of a minus 1 to the 1/2 power. And then the 1/2 becomes the coefficient, so we have 1/2 ln a minus 1. And again, we have no distribution idea with natural log through this binomial. Let's apply the same kind of idea with the radical here. We have natural log of a fraction to the 1/2 power. Now the fraction becomes a coefficient. And now we have the log, the natural log of a quotient. And so we have, looks like we're going to have the difference of logarithms. So this becomes 1/2 times. Now, I have to introduce a parenthesis here. This is the purpose of showing this particular problem. You see, here we have 1/2 times a single item, a single term. But once we go through that property of the logarithm of a quotient is the difference of two logarithms, we're going to end up with two terms here. And we want to take half of those two terms. So it's 1/2 introduce parenthesis, you see 1/2 times ln numerator minus ln denominator. And we can go further with this problem. In fact, we can go quite a bit further. Let's come up here and work with it a little bit more. We're not finished expanding here by any stretch. All right, I'm just going to repeat that step. It's 1/2 times ln x squared. By the way, in this situation, if you feel like stopping the tape and trying these problems on your own and then rolling the tape, please do that. The experience is your greatest ally in learning how to do these problems well. All right, at any rate, we have 1/2 times these two items in parentheses. And we can go ahead and multiply that 1/2 times each of these terms. See, the distributive property works here. This is just a real number times two items. You see, so we can do that. Or we can do this. We can say this is 1/2 times, now using the power property here, this is 2 ln x, and this is minus 3 ln y. You see, and now we can distribute if we'd like at this point. So we would have 1/2 times the first term minus 1/2 times the second term. See, I'm writing this step in for emphasis. We could probably see 1/2 times each of those terms rather easily, but for emphasis here, the 2's go out and we have ln x, and then here we have minus 1/2 times 3, well that's 3/2 times ln y. Let's go in the other direction with using our properties. That is, in these problems, we were taking a rather condensed version of a logarithmic expression, and we were expanding. Now let's sort of take an expanded version and contract. So let's bring these two together. We have the difference of logarithms, and so that's the logarithm of a quotient. So it's the log of the first item over the second item as items within that fraction. So the logarithm of this as the numerator and that as the denominator, using our quotient rule. All right, when we see coefficients involved in an expression like this, go through and use the power property and write these coefficients as exponents like this. This becomes ln 8 squared, then plus ln z to the 5th. You see, I'm just moving these coefficients to a position of an exponent. You see, and now we can, after doing that, we can bring these together either either using the quotient property or the product property. All right, here we have the sum of two logarithms, and so we're going to use the product property. So we have the natural log of the product of 8 squared times z to the 5th. Now 8 squared is 64, so this is 64 z to the 5th. Let's condense here. Now the first order of business, once again, is to take the coefficients and move them to a position of exponent. So we would have here ln 3 to the 4th power. Now on this one, it turns out that it doesn't make any difference whether I think of moving -2 to that position and putting a plus sign here, or leave the plus sign here and just move the 2 up there. You see, but what you don't want to do is put -2 up there and leave that as a negative. Then you're changing the problem. All right, but so either of those techniques works. I kind of like the idea of just leaving the minus sign here and put the 2 up there. So we'd have this. All right, now we begin to bring things together. There are a couple of ways of handling this situation with a minus sign. Now, I'm going to show you one of them that is real safe. Let me write 3 to the 4th as 81. That'll make things a little easier. All right. I'm going to factor -1 out of these two. And look at what it does for me. I have ln x squared plus ln y. And in parenthesis, I can use the product property to write this as ln x squared y, you see. And now, because I have the difference of two logarithms, that's the logarithm of a quotient, so it's ln 81 over x squared y. Now let me show you a faster way to look at this. It'll turn out that when you're in a form like this, when you're in an expression where all of your coefficients are either plus or minus 1, that you can just take all of the items preceded with a plus sign are going to produce factors that are in the numerator, you see, of a fraction, and all of the items preceded with a minus sign are going to produce factors that are in a denominator of a fraction. So this is preceded with a minus sign, x squared appears in this denominator. Preceded by a minus sign, the y appears in the denominator. So we could very quickly go from this form to this form if we know that technique. In this problem, once again, we're going to take coefficients and clear them to the point of exponent, a traditional point of exponent. This is ln 3 squared, then minus, I'll leave the minus sign here, the 1/2 goes as the exponent over there, so it's ln x squared plus 1 to the 1/2 power. Now, 3 squared is 9. I'm going to burn a step here and simplify just a little bit. And it's important to understand that the 1/2 exponent means that we have a radical. So this is the square root of x squared plus 1. Now we have the difference of logarithms, which implies the logarithm of a quotient. So it's the logarithm of 9 over the square root of x squared plus 1. A lot of times with problems in this situation, there are several right ways to work the problem. And I want to show you a problem, and I want to show you 2 ways to work it. A lot of times it's the case where if your study partner or you see someone else work the problem differently, you think that your method is wrong. Well, that's not always the case. And even with the things that I've done here, if you have another method of working these that works out to the same result, it's probably the case that you've done it correctly. All right, here we're starting with 3 times ln 4 plus ln x. Our choices are to work within the parenthesis first or to multiply 3 times all those terms. Now, if we work within the parenthesis first, then this would be, let's see, by the product property, ln of the product of 4x. So we have ln 4x. And now the 3 moves to a position of exponent. The danger here is to leave off the parenthesis. Just realize that this 3, when it moves to the exponent idea, it's the exponent on the 4x and not on just the x. You see, so be careful about that. Now you apply that exponent to both terms and we have 64x cubed following the natural log. The other approach is to go ahead and distribute 3 through the parenthesis, so we would have 3 ln 4 plus 3 ln x. And then those 3's would go into the position of exponent, so we have ln 4 cubed plus ln x cubed. 4 cubed, of course, is 64, so we have the natural log of 64 times x cubed as we expected. Here's a problem that allows us to use the properties of logarithms in a somewhat different way. It says if log in base 5 of 2 is approximately this value and log 3 in base 5 is approximately this value, then we'd like to evaluate a couple of expressions. If we want to evaluate log 6 in base 5, now we don't know the value of log 6, you see, in base 5. All we have is information about log 3 and log 2. The trick is to rewrite this in terms of log 3 and log 2, which we know the value of. So we'll think of this then as log of, let's see, now 6 we can think of as 2 times 3, you see, and then we have the logarithm of a product. So using our product property, it's the log of 2 plus the log of 3. in base 5, and we have values for those. We have approximations. Let's see, log 2 is the 0.431, and log 3 is 683. Adding, we find it to be 1.114. So we have found the log of 6 in base 5 using this method. This one is a little more challenging. We want the log of 9/2 in base 5. Now, again, the trick is to rewrite this expression using log 2 and log 3 in base 5. So we think of it like this. Using our quotient rule, it's the log of 9 minus the log of 2. Now we think of 9 as 3 squared, and the 2 in the 3 squared becomes the coefficient of the logarithm. And now we can make the appropriate substitutions. Log 3 in base 5 has this value. Log 2 in base 5 has approximately this value. And evaluating, we find this. Now, let's understand what we have here for this 0.935. What we are finding, and when we find the log of 9/2 in base 5, we are finding the exponent that can be applied to this base in order to give 9/2. That is, 5 to that exponent is 9/2.